Black holes. Just the name is enough to send shivers down your spine. These mysterious and powerful entities have fascinated scientists and the general public alike for decades. They are regions of space-time where gravity is so strong, nothing, not even light, can escape. Imagine a cosmic drain, relentlessly pulling everything nearby into its depths. Spooky, right? But black holes are more than just frightening objects in the vast cosmic dark. They are like cosmic laboratories, pushing the boundaries of our understanding of the universe. By studying these enigmatic objects, we can unlock secrets about gravity, the nature of space-time, and maybe even the fate of the universe itself. One of the most fascinating things about black holes is how they challenge our everyday intuition. Think about throwing a ball up in the air. It goes up, slows down, and then falls back to Earth. But near a black hole, the rules of the game change dramatically. The immense gravity warps the fabric of space-time itself, creating a cosmic whirlpool from which there is no escape. It's like trying to swim upstream against a current so strong it pulls you backwards no matter how hard you struggle. This warping of space-time leads to some mind-bending phenomena. For instance, time itself behaves differently near a black hole. If you were to watch someone fall into a black hole, it would appear to you as if they are slowing down and eventually freezing in time as they approach the event horizon. Meanwhile, the person falling into the black hole would experience time normally, but they would see the outside universe speed up dramatically. This is due to the extreme gravitational time dilation caused by the black hole's immense gravity. It's a concept that stretches the limits of our imagination and challenges our understanding of reality. Scientists are continually studying black holes to learn more about these incredible phenomena. They use advanced telescopes and instruments to observe the effects of black holes on their surroundings, such as the bending of light and the movement of nearby stars. These observations help us piece together the puzzle of how black holes form, evolve, and interact with the universe. One of the most exciting recent discoveries in black hole research is the detection of gravitational waves. These ripples in spacetime are caused by the collision and merging of black holes, and they provide a new way to observe and understand these enigmatic objects. By studying gravitational waves, scientists can gain insights into the properties of black holes, such as their mass and spin, and learn more about the extreme conditions in which they exist. Black holes also play a crucial role in the evolution of galaxies. They can influence the formation of stars and the distribution of matter in their host galaxies. Some supermassive black holes, found at the centers of galaxies, can even regulate the growth of their galaxies by emitting powerful jets of energy that can affect star formation. As we continue to study black holes, we are constantly reminded of how much we still have to learn about the universe. These mysterious objects challenge our understanding of physics and push the boundaries of what we know about the cosmos. They are a testament to the incredible complexity and beauty of the universe, and they inspire us to keep exploring and seeking answers to the many questions that remain. So the next time you hear the term black hole, remember that these cosmic enigmas are not just objects of fear, but also windows to the universe, offering us a glimpse into the fundamental workings of nature. The immense gravity warps the fabric of space-time itself, creating a cosmic whirlpool from which there is no escape. It's like trying to swim upstream against a current so strong it pulls you backwards no matter how hard you struggle. Black holes are truly one of the most fascinating and awe-inspiring phenomena in the universe. Now, you might think that black holes live up to their name, shrouded in eternal darkness. These cosmic giants, with their immense gravitational pull, are often depicted as voracious entities that consume everything in their path, including light itself. The very term black hole conjures images of an abyss from which nothing can escape. But here's where things get really interesting. Contrary to their ominous reputation, black holes might not be as black as we once thought. This revelation has turned our understanding of these celestial objects on its head. In the 1970s, Stephen Hawking, a brilliant physicist, proposed a revolutionary idea. Black holes aren't entirely black. Enter Hawking radiation. This groundbreaking theory suggested that black holes emit a faint glow of particles, challenging the notion that nothing can escape their grasp. This mind-bending concept suggests that black holes slowly leak energy over time due to quantum effects near their event horizon, the point of no return. The event horizon is the boundary beyond which nothing can escape the black hole's pull, not even light. It's like the black hole is slowly evaporating, radiating away its mass in a faint glow of particles. This process, though incredibly slow, means that black holes are not the eternal prisons we once thought they were. Think of it like this. Imagine a pot of boiling water. As the water heats up, steam rises from the surface, carrying away tiny amounts of water in the form of vapor. The steam rising from the pot is like Hawking radiation, carrying away a tiny bit of the water's energy over time. Just as the pot of water will eventually run dry if left boiling, a black hole will lose its mass over eons through this radiation. In the same way, black holes slowly lose mass through this process. This gradual loss of mass has profound implications for the life cycle of black holes and the fate of the universe. Hawking radiation has profound implications for our understanding of black holes. It challenges the very foundations of what we know about these enigmatic objects and forces us to rethink the laws of physics as they apply to the cosmos. If they're constantly losing mass, does this mean they eventually disappear entirely? The idea that black holes could one day vanish into nothingness is both fascinating and perplexing. What happens to the information that falls into a black hole? This question touches on the very nature of reality and the fundamental principles of quantum mechanics. These are questions that keep astrophysicists up at night. The mysteries of black holes continue to captivate our imagination and drive scientific inquiry, pushing the boundaries of our understanding of the universe. Black holes often get a bad rap in science fiction, portrayed as cosmic vacuum cleaners sucking up everything in their path. Movies and TV shows love to depict them as these monstrous entities that can devour entire star systems in the blink of an eye. This portrayal, while thrilling and dramatic, is far from the truth. But the truth is a bit more nuanced. Black holes are indeed fascinating and powerful, but they don't roam the universe indiscriminately consuming everything in their vicinity. They are bound by the same laws of physics that govern other celestial bodies. While their gravity is undeniably strong, it's not some irresistible force that gobbles up entire galaxies. In fact, black holes can coexist peacefully with other celestial objects. They only become dangerous if you venture too close to their event horizon, the point beyond which nothing can escape their gravitational pull. Think of it this way. If our sun were suddenly replaced by a black hole of the same mass, Earth wouldn't be sucked in. The gravitational pull on Earth would remain the same because the mass hasn't changed, only its form. The planets would continue their orbits as if nothing had happened, albeit in a much darker solar system. Instead, it would continue to orbit the black hole, just as it orbits the sun now. The only difference would be the absence of sunlight, which would have profound effects on life on Earth, but the gravitational dynamics would remain unchanged. The key difference is that a black hole packs all that mass into a much smaller space. This incredible density is what gives black holes their unique properties, such as the ability to bend light and create gravitational lensing effects, where light from stars behind the black hole is bent around it, creating a ring-like appearance. The strength of a black hole's gravitational pull depends on its mass and how close you are to it. The closer you get, the stronger the gravitational force becomes, eventually reaching a point where not even light can escape. Just like with any other object in the universe, gravity weakens with distance. So a black hole's influence is only significant if you are relatively close to it. At a distance, its gravitational pull is no different from that of any other object of the same mass. So, you don't need to worry about black holes lurking in the shadows of the cosmos, ready to devour our planet. They are not cosmic predators lying in wait. They are simply another fascinating aspect of our universe. However, the extreme environments around black holes can be quite chaotic. The immense gravitational forces can cause nearby material to spiral inwards, creating some of the most energetic and dynamic phenomena in the universe. Gas and dust spiraling into a black hole form what's called an accretion disk. This disk is a swirling mass of material that heats up as it gets closer to the black hole, due to the immense gravitational forces at play. This disk heats up due to friction, emitting intense radiation across the electromagnetic spectrum. These emissions can be so powerful that they outshine entire galaxies, making black holes some of the brightest objects in the universe, despite their name suggesting otherwise. Studying black holes is no easy feat. They are incredibly distant, and, by their very nature, invisible to traditional telescopes that rely on light. So how do we even know they exist if we can't see them directly? The answer lies in their effects on their surroundings and the gravitational forces they exert. Remember that accretion disk we talked about? The intense radiation emitted by the superheated gas and dust acts like a cosmic beacon, alerting us to the presence of a black hole. Astronomers also study the motions of stars orbiting around invisible but massive objects. By analyzing these orbits, they can infer the presence of a black hole and even estimate its mass with remarkable accuracy. One groundbreaking project that has revolutionized our understanding of black holes is the Event Horizon Telescope. This global network of telescopes works together to create a virtual telescope the size of Earth, giving us the sharpest views of these enigmatic objects ever seen.